Hello, this is Mr. Ranger. We are talking about chemistry 1123, which is the third pace. I'm not going to cover the first few pages. That's pretty easy about the different phases of matter and the kinetic theory of matter. But I want to dive in on pages 2 through 4 because there are some concepts there that we really need to talk about. We want to talk about thermal energy. Now, when you think of the word energy, maybe you think of, oh, I've got a lot of energy today. I just want to go do something. And we think of having a lot of ability to work or to do something, to run. And I've got a lot of energy. We talk about little toddlers as having high energy, right? And then there might be a day that you get to the end of the day and you're exhausted and you say, oh, I just don't have any energy to do my homework tonight. And you just want to lay on the couch, right? So energy is the ability to do work and to move things. So movement has a lot to do with energy. And that's what we call kinetic energy, okay? In chemistry, we're going to learn later, there's also chemistry stored in the bonds. We're going to get to that later, don't worry about that. But when you put those two together, the total energy is called thermal energy. Now, kinetic energy in a sample, let's say it's water or some kind of a liquid or anything, and you probably noticed this, if you have a cup of hot chocolate or coffee and you set it on the counter for 20 minutes or an hour, what happens? It goes from being nice and hot to reaching the same temperature as the room around it, right? What's happened? It has lost some of the thermal energy. And when that is moving, when thermal energy is moving from something hot to something cooler, from high energy to low energy, we call that movement heat. Okay, so the heat, by definition, is thermal energy, and it always moves from a warm body to a colder body. Now, there's a significant difference between heat and temperature. Thermal energy is the total amount of energy that all the particles have and that they could transfer. So I'm picturing here, we have a flask, and that would be maybe the size of a coffee cup, and it just has that kind of funny shape to it. Let's say the water in there is 80 degrees. That's a little warmer than room temperature, but around room temperature. And then let's say we have a bathtub full of warm water, 80 degrees. They're the same temperature, okay, but the bathtub has a lot more thermal energy because it has a lot more particles at that temperature of 80 degrees. And so there's a lot more energy in there. Think of it this way. If you left the two in a kind of chilly room, they would eventually both reach room temperature, but the cup of coffee, in this case this green flask, wouldn't give off a lot of thermal energy. You probably wouldn't notice that the room had changed temperature. But if you poured hot water into a bathtub, over time that water would heat up that room. Maybe you've noticed that if you've ever been to a sauna or a swimming pool, an indoor swimming pool in like a hotel, and the heat just from the swimming pool water is radiating into the air and heating up the air, okay? So that is thermal energy heating the air. Temperature would be the average kinetic energy of the particles that make up the substance. We obviously use a thermometer to measure temperature, and usually in chemistry, we're going to start with Celsius, and a lot of times we're going to use a Kelvin temperature scale. Maybe you remember that from physical science. If they give it to us in Fahrenheit, we usually end up having to convert it to Celsius and or Kelvin. Now, I want to point something out here about heat. And you see this in the margin on page 3. It talks about energy can be measured in joules and also in calories. And they do refer to a Newton somewhere on the page, so they give a definition here, the amount of force required to accelerate. You know what? Put parentheses around that and basically ignore it, okay? That's physics. It's just like one of those fun factoids that they're just kind of throwing in there. But do not worry your brain about trying to remember that. That has nothing to do with what we need to know in chemistry, right now anyways, okay? So heat can be measured in calories or in joules. Most often, later, we're going to stick with joules. I'm going to give you a little heads up here. We use calories, particularly if we're talking about water. And at the bottom of this little chart, so this is kind of important, 1 calorie is about 4.184 joules. That is an important conversion that we are going to have to use as we solve some problems in this pace. Now, you're probably, when you think of calories, you might be thinking about, oh, I need to watch my calories so I don't gain weight. Or you look at your breakfast cereal and you're reading all the stuff on the side and it tells you how many calories per serving. Excuse me, a calorie of that type is actually capital C. Isn't that confusing? Capital C calorie is equal to 1,000 of the smaller chemistry calories. And actually 1,000 would be kilo, wouldn't it? So kilo calories are the same as the calories that we have on food items. Now at the bottom of page 3 in the box, they have energy value of selected foods. Again, that's just for fun. That's a factoid. You're not going to have to use that. Don't worry about that. It's just kind of for fun. They're showing the comparison between kilocalories and kilojoules and types of food. Literally, your body, when you eat food, it breaks that food down and releases energy, and it burns some energy. All right, real quick here. Sometimes the way they word things here in the chemistry piece, it's a little confusing. It says an older system measures heat in units called calories, abbreviated cal. A calorie is the amount of heat required to raise the temperature of 1 gram of water, and that's important. 1 gram of water, I don't know why they say from 14.5 degrees Celsius to 15.5 degrees Celsius. That just really adds a level of complexity that's not necessary. The bottom line is you're raising it 1 degree Celsius. That's all you need to know. So 1 gram of water, that's pretty small, okay? That would be like 1 cubic centimeter. And you put 1 gram of water in there and raise it 1 degree Celsius, and that would be 1 calorie. You could probably just by, if you had that in a little container and you put your fingers on there, you could probably add 1 calorie of heat from your fingers through the glass to heat up that little bit of water 1 degree Celsius, okay? So I wouldn't worry about this, okay? Ignore that. We talked about some of these other things, kilocalories, and that's also the same as the capital C calorie. All right, let's look at the formula at the bottom of page 3. This is an important formula that we're going to use in this section of the PACE. Notice we have this Q. I don't know why heat is the letter Q. I just can't explain that. We just need to memorize it. Q is heat. And then M is the mass. And it says delta T is the change in temperature. So notice we have M right up against delta T. So that means we have two things here, M and delta T. And we are multiplying those two things together, the mass times the delta T. Now I want you to notice this is for water, okay? So we can find the mass of the water and use delta T, and we can find the answer to come out in calories. Now you say, well, what is delta T, Mr. Enger? Well, this is an important formula that they have on the lower right-hand corner of page 3. The symbol that looks like a triangle here is the Greek letter delta. And we're going to see that all the way through chemistry. We see it a lot in physics. Sometimes we see it in math courses. It means the change in something. So you could read delta T as the change in the temperature. And to find that change, we always take the final temperature and subtract the initial temperature. So in this case, we're saying we're going to change the temperature from 80 degrees and let it cool off until it's 20 degrees Celsius. So in that case, we have changed the temperature 80 degrees. Okay? I shouldn't say we lowered the temperature. We actually raised the temperature in this case because the initial temperature was 20, the final temperature was 100. Sorry about that. So we're raising the temperature by 80 degrees. If it had been the other way around, this would be a negative 80 and we would be decreasing the temperature. All right, I think that's enough to get you through this first section. I'm going to come back and we're going to do a video for specific heat.